Unit 5 is solutions. And unfortunately, I don't mean answers. Okay. Solutions. We're going to talk about solution concentrations, different ways to represent solution concentrations, and how to perform calculations involving solute, solvent. We have to begin with some just some terms. These aren't going to be on the exam. You're not going to have define solvent, define solute. This is more just for you to get familiar with some of the verbiage that we'll be using. For a binary solution, okay, a solution that contains only two components. One of the components is termed the solvent. This is the component present. This is the component present in the greatest amount. Can you guys see that back there? Is it dark enough? And the solute. This is going to be the component present in the least amounts. It's possible to have more components than two in a particular solution. So it's possible to have a particular solution that has many different solutes, but it's only possible to have one solvent. Generally speaking, what we're going to be talking about is water. Water's our solvent. Aqueous, we already know what that is, right? We saw that in the last unit. Aqueous means in water. Dissolved in water. We saw this in particular with our precipitation reactions, where we did our balanced formula equation, our total ionic equation, and then our net ionic equation. That's what we saw. Concentrated and dilute, when you can look at that, solution has a relatively large amount of solute. What's relative? We're going to skip right to miscible. Miscible and immiscible are terms used to describe when you mix liquids together. Okay? When you mix two liquids together, you don't use a term like dissolve. Say you have alcohol and water, or ether and water. These are two liquids. When you mix them together, you don't use a term like dissolving. Dissolving generally is reserved for solids interacting with liquids, just what you're familiar with. When you're talking about two liquids, or mixing two liquids, you use terms like miscible and immiscible. If the two liquids are soluble in each other and they form one continuous layer, they're miscible. If they separate out, like oil and vinegar would, they're immiscible. So, miscible, the two liquids form a continuous layer. Okay, basically they mix together. They mix. Mix isn't technically the right term, but they mix together and they're soluble in one another. Immiscible is when the two liquids form two distinct layers. I.e. Oil and vinegar. Oil and vinegar. Separate out. They're not miscible. Saturated and unsaturated. A saturated solution contains the maximum number of solute in a specified volume of solvent at a given temperature. It's very important, at a given temperature. So a saturated solution contains the maximum amount of solute in a specified volume at a given temperature. Okay? You can best relate to this solubility and saturation and unsaturation by using an example like a cup of coffee. If you take a cup of coffee and you heat the water up really hot, you can dissolve more coffee into that hot cup of water. Now the volume is specified and fixed at whatever a cup is. As the coffee begins, and you take a sip of it and you say, wow, that's strong coffee, right? Because there's a lot of coffee dissolved in it. As the coffee cools down, the temperature changes, and the solubility of the liquid as it's cooling changes. And it actually gives back some of that coffee that it can no longer hold in solution as the temperature is cooling down. So that's that stuff that's always in the bottom of a cup of hot chocolate or a cup of coffee when you're done, because you set it down and you let it cool down. So this concept of solubility and saturation is temperature dependent. I think you can make this statement that hotter solutions are always have a greater solubility. They can always hold more solute particles as you heat them. Of course, you can only get to a certain level on the temperature of the liquid, because then it'll boil away. Then we have probably the best definition of all, unsaturated solution. Unsaturated solution is any amount of solute below the saturated. This is any amount of solute below the concentration in a saturated solution. Love that definition. You know, here's your maximum amount at a temperature is saturated. What's unsaturated? Well, any amount below that. You can generally tell a saturated solution. In order to find it, there's tables, there's references that tell you how much of a particular solute will dissolve in a particular volume of water or lots of other liquids. But generally, you get to saturation, you just take your volume of solvent and you start dissolving the solute in it. So let's say that we're taking water and we're dissolving salt in it. You put some salt in it and you stir it and it dissolves. You put some more salt in it, you stir it, it dissolves. Then you put a little salt in it and you see that there's actually a little bit of salt collecting on the bottom of the glass. That's when you know you're at saturation. When the solution can't take any more. Okay, and we'll see in just a minute that that's really not. It's really kind of a dynamic process. The salt's actually dissolving and precipitating out at the same rate, so it looks like it's just staying constant. Okay? So again, these are just some terms that we'll be using in lab. We'll be using them, you'll see them in the homework. As far as an exam question, I don't think that you're going to see one that say define miscible, A, B, C, D. Okay? But it's important that you know these terms and you're able to understand, the communication. Okay. Hydrogen bonding. We know that when we have covalent compounds are made up of nonmetals, right? And when you have two nonmetals, elements that are on the right of our periodic table, our dividing point, on the right, when you have two nonmetals that aren't the same nonmetal, then the sharing of the electrons between them is unequal, and you have yourself a polar bond. Water is an excellent example of this. All right. Each of the bonds in water, it's an OH bond. It's covalent because they're both nonmetals. I know that H is located in group 1, where the metals would be. But the only reason why it's there is because it has an electron configuration of 1s1, which puts it in the group 1. But it's certainly not a metal. Hydrogen is not a metal. Hydrogen and oxygen are both nonmetals. Therefore, we have a covalent bond. They're not the same nonmetal. In other words, they're different nonmetals. So we have a polar covalent bond. We check our periodic table and we see that oxygen is closer to fluorine than hydrogen is. So oxygen wins the tug of war. And we end up with these slight regions of positive and negative. Now again, this is nowhere near a fully developed plus or minus charge that you would see in an ionic compound where the electrons actually transfer. Because the oxygen is more electronegative, it distorts the electron's path around the two nuclei, and it distorts it more toward oxygen, less toward hydrogen. It still goes around hydrogen, but it doesn't spend as much time around hydrogen, and therefore we get these slight regions of positive and negative. And each one of the bonds behaves in this manner. Now if we look at oxygen, that's in group 6, we see oxygen has 2 bonds, 2 lone pairs. If we look at our table of geometries in chapter 3, we see that this is bent or angular. We can call it angular, right? So this is actually the shape of the water molecule. And we can actually draw polarity vectors in here. There's actually a magnitude on the pulling power, on the tug of war here. And we draw those by simply drawing an arrow in the direction that the electrons are being pulled. So there's a force vector across it here on this side indicating, hey, this is the positive end. And I draw my arrow in the direction that the electrons are being pulled. And if I look at these, what we call polarity vectors, I see that they come in at an angle, and when they hit, they keep going. Imagine 2 cars coming in at an angle. If they hit each other this way, they're going to keep going in that direction. So there's a net result of those force vectors. That's why this is polar. That's why the molecule is polar. Had we had something like we had in the past on our lab, a linear arrangement, again, oxygen's closer than carbon, so now our vectors are going this way. You see how they're pulling at 180 degrees? They cancel each other out. That's why the linear arrangement, even though it has polar bonds in it, will be a nonpolar molecule. Now I told you that we only really needed to be concerned in this class with structures that were linear or tetrahedral in terms of them being nonpolar. Okay? So this is bent, which means it is polar overall. So we know water is a polar covalent molecule. If you have other water molecules around, which you clearly would have in any glass of water, right? Billions and billions and billions and billions of water molecules, these water molecules can align and interact with each other in an opposites attract fashion, in an electrostatic fashion. We refer to this as non-covalent because they're not sharing the electrons. What we have here is a permanent pole in our water molecule. And if you put it around other molecules with permanent poles or dipoles on them, the dipoles will align, negative areas to positive areas, and they'll interact intermolecularly, inter. I always remember intramural sports, within the school, between the schools. So, intermolecular is between the molecules. These are not intra, within the molecule. And they can interact in just about all possible configurations. Just about anything you can think of, this will happen. And these guys will interact. When these bonds involve a hydrogen atom, we call it hydrogen bonding. It's the most common in water. This is why water has so many unusual properties. Very unusual. Okay? This is what gives water its surface tension. It's what gives it its high heat capacities. Think about water. What's the mass of water? 18 grams per mole, right? 18 grams per mole. Everything else around 18 grams, smaller, bigger, is a gas at room temperature. Look at O2. What's O2? 32 grams per mole, right? N2, 28 grams per mole. Methane, 16 grams per mole. Every other substance that we know of around that molar mass, okay, compounds, are gases at room temperature. Obviously, there are elements that are not, right? It's very unusual, and it's all due to hydrogen bonding. Surprisingly, water is a really good insulator, okay? Land that's in contact with water, you don't see huge temperature fluctuations over the course of the seasons. You can have a temperature. Now you gotta dig down. Get 6 or 8 feet into the ground, and you'll see that the temperature of the land remains relatively constant through the winter and summer months. And that'd be unlike a place like the Sahara Desert, where it can fluctuate 100, 120 degrees from night to day, Fahrenheit, right? Because it's a tremendous insulator. When the land gets warm, the water pulls the heat off it. When the land gets cold, it pulls the heat from the water. I mean, think about how much heat the ocean can store. How much energy do you think you'd have to add to the Atlantic Ocean to get it to raise 1 degree Celsius? I mean, just an enormous amount of heat. So it can store heat very, very well, and it can give it up and take it on quickly. Okay, so this is hydrogen bonding. Okay, first of all, you have to have covalent compounds. All right, for hydrogen bonding, they have to be covalent, and they have to involve water. So we can have a bond with hydrogen where X can be nitrogen, oxygen, or I think we have one more, fluorine. There's more, but let's just concentrate on them. So we're going to be looking for hydrogen bonding in NH bonds, OH bonds, and FH bonds, HF bonds. Okay? This happens a lot. Right? You have these kinds of electrostatic interactions all the time. Okay? Anytime you have polar bonds, you have the possibility of having these kinds of interactions, these non-covalent interactions. But when the bond involves hydrogen, they simply call it a hydrogen bond. And they give it its own name because of the extensive nature of water, that it exists in water. Okay? Technically, each water molecule could form 4 hydrogen bonds, right, to adjacent water molecules. It could form it to 4 different ones, 2 different ones, whatever. It's not 4, though. It can have a possibility of 4, but it doesn't form 4. It's like 3.2 or 3.3. Don't ask me how you get a 0.2 of a hydrogen bond, but that's average. And in water, these are constantly breaking and forming and breaking and forming. Okay? H bonding. This plays a role also in the process of dissolving. Water is sometimes called the universal solvent because it has an ability to dissolve a lot of different ionic compounds. So let's look at something like NaCl. We saw this structure briefly. Just going to draw it. It is a body-centered cube. So these would be our Cl minuses. And then in between, we have a little Na plus. And again, this is a body-centered cube. It's not, spatial orientation is not exact in this two-dimensional drawing. But what we see is that, and this is consistent with any ionic compound that you put in water. Once you put that compound in water, the water molecules will orient in such a manner. Around the positive ones, you'll see the negative oxygens oriented inward. So the water will come in and it will surround these little sodiums in this kind of fashion with the negative regions around it. And the water will pluck that sodium ion off the crystal structure, and then it will surround it. So we'll have this little sodium plus, and then it will be surrounded by these water molecules. But they'll always be oriented with their negative side in because the sodium is positive. Okay? And this is called a solvation sphere. And this can be several layers thick. And the thicker it gets, the less likely the sodium plus will be able to feel the Cl minus again and get back together and form the crystal. But as you evaporate the water, you decrease those solvation spheres. Now the sodium pluses can find the Cl minuses again, and they can get together and recrystallize out the NaCl crystals. And that's what happens when you evaporate the water. You would expect, and that is what happens, the opposite with the chlorine. Slightly positive regions of the water molecules now surround the chlorine ions and pluck the chlorine ion right off from the crystal structure and surround it in much the same way. you have these little positives all the way around. And again, these solvation spheres can be several layers thick. All right? And remember, this water is hydrogen bound to other waters extensively out here. So this network, it's almost like a huge fish net, right? You have this huge network of all these intertwined and interconnected water molecules, and some of them are hooked around an ion, and the net just kind of pulls those ions off the crystal and then surrounds it. Okay? And for ions that are produced in solution, these are able to conduct electricity, because you have to have ions in solution to conduct electricity. So anything that produces ions in solutions is called an electrolyte. An electrolyte. Okay, and the key term or the key action there is the production of ions. Okay, so most ionic compounds would be considered electrolytes because they dissolve in water. All right, there's really a difference between ionizing and dissolving. Okay, they're kind of related, but they're still different. When you ionize, you dissolve, but you actually produce ions in solution. And you test ion production by whether or not the solution will conduct electricity. If it conducts electricity, that must mean there are ions in solution. That means that that particular compound ionized. Most ionic compounds will ionize in solution. The exceptions are those ones given by our solubility rules, the ones that don't break apart. Okay? If you don't break apart and you stay a solid in solution, you don't produce ions in solution, you don't conduct electricity, you're a non-electrolyte. Okay? Everybody good with that? Okay. You can also dissolve covalent compounds. How would we know covalent compounds again? We would look at the fact that there are no metals present. When you have a covalent compound, like, let's say, I think they use a disaccharide in here. Yeah, let's use a sugar. Okay, this contains nothing but carbons, hydrogens, and oxygens. This is a covalent compound, and it's a disaccharide. It's not named, could be sucrose. It's a sugar. Sugars dissolve in water, and we're all familiar with that. We've all done it. You take a teaspoon of sugar and you can dissolve it in water. But they don't produce ions. The solution won't conduct electricity and is therefore a non-electrolyte. But in the dissolving process, it's still basically the same as what happens to the ions here. Only with the covalent compounds, the water molecules actually surround the entire covalent molecule. And they create a solvation sphere in and around the molecule. In the case of sugar, we'll see in our biochem lectures that sugars are actually polyhydroxy, many OH groups, polyhydroxy aldehydes or ketones. And so our sugars have a lot of OH groups. Well, guess what? OH groups are polar. So the water interacts at those polar OH groups. And that's how it dissolves those particular sugars. The process is the same in that water molecules surround each of the species, whether it's ions or a covalent compound. The difference is with the ionic compounds, they produce ions in solution that are capable of conducting electricity. And the covalent compounds do not produce ions in solution. Covalent bonds are too strong. They're too strong. The water can't break those. Okay? Just qualitative questions on this. I don't think you're obviously going to have to draw this. Just some qualitative ones. And we're going to do a lab on this where we test conductivity of various solutions. Because, I mean, you have to understand, many years ago, really not that many years ago, they had to figure out different things. They didn't know the things that we knew today. And one of the things they could do was try to pass a current through various solutions. And one of the anomalies was, how come this solution conducts electricity and this one doesn't? And this led to our theories about ions and conducting electricity and covalent versus ionic compounds. So it's all kind of interrelated. Okay, solubility. Solubility, good rule of thumb, likes dissolve likes. What does that mean? That means that polar compounds will dissolve polar molecules and nonpolar compounds will dissolve nonpolar molecules. Okay? You guys have seen this. You've seen examples of this. You've grown up with it. Okay? You go out, you run around, you get a grass stain on your pants. Right? Then what happens? Your mom takes your pants that now have a grass stain in it, put it in the wash, and they wash it. And guess what? Your pants come out and the grass stain's still on there, right? Because by and large, the grass stain is organic in nature. And you're trying to take it out with water. Doesn't work. So what we do is we add various things to our water, like detergents, in an effort to make it more like the stain, so that it will take the stain out. Or now, alternatively, they have these new things that you spot on the stain to make the stain more like the water. Either way, you're trying to make one more like the other, so that they will dissolve in each other and you can get the stain out. Okay, so this is likes dissolve likes. That's it qualitatively. Solubility is actually a number. Okay, it's a quantitative maximum of solute, and it's very similar to our saturated solution. In fact, when you have a saturated solution, you've reached the solubility of that particular solvent. The solubility is exactly the same definition. It's the maximum amount of solute that can be dissolved in a specified volume of solvent at a given temp. Once you've reached saturation, you've reached the limit of the solubility. The solution, that volume of solution, simply can't accommodate any more solute. If you want to add more solute or get more solute to dissolve, you have to do one of two things. You have to add more solvent, i.e. more water, or you have to heat the solvent. One or the other. Okay, this is our solubility. So solubility is actually a number. It's just a single number and it's reported. There's a solubility of NaCl in water. There's a solubility of sugar in water. These are in reference texts. And sometimes you need to know that stuff. Okay? Alright. So we have some of our terms down. Why do we need them? Why do we need them? Well, we have to do some calculations, unfortunately, right? More math. Boo. Pretty soon you'll be done with the math, though. Another couple of units. We'll put the calculators away, and we'll get into the organic and the biochem. You won't need them again until the final. Solution concentration. Solution concentration. This is generally going to be some type of expression that relates some amount of solute per volume. Volume or amount? Amount of solution. I don't like that. Let's say volume of solution. Okay, all we're going to do is do different or find different methods for expressing this ratio. Okay, and we have 3 or 4 different methods. You're going to have to memorize the formulas. I need the formulas on the next exam. Okay, but at its core, this is what we're trying to show. Concentration, by definition, is how much solute do I have contained in a specific volume of water, or solution, not water, solution. Water would be the solid. Okay, we have a couple of different ones. I'm just going to do some examples. We have percent M over V, percent mass volume. This is going to equal grams of solute over milliliters of solution. Times 100. We also refer to this as parts per hundred. All right, parts per hundred, but we generally don't call it that. We call it percent mass volume. Percent mass volume. Now, you have to be careful because these 3 things that we're dealing with, solute, solvent, solution, I mean, they all kind of sound the same. You know, they all start with SOLs. So you got to be cognizant of that. You got to understand and realize that. Notice this is solution, right? This is total solution. Notice that's total solution, yes?
So is that a solution, solute, and solvent?
Yes, that's exactly what I was going to say. This is total solution. So what did we say solution was at the very beginning? The first thing I wrote down, solution is solute and solvent, right? It's both. Okay? When you put solute into water, for example, and let's say that you had 100 mils of solution. If you have 100 mils of solution, you do not have 100 mils of water. So, do you understand that? Because when you take water, and you take a beaker or a flask, and you put solid in it, 5 grams, 10 grams of sugar, whatever, and then you start dumping water in it, and you dilute that thing up to 100 mils. You didn't add 100 mils of water because the solid takes up space in the solution. All right? So, this is not, when you say 100 mils of solution, it's not 100 mils of water. It's always something less than 100 mils. It has to be. Okay, I think these particular questions or calculations would be very straightforward. They're going to be straightforward. Okay, you're going to know which number goes in the top versus which one goes in the bottom, because you can let your units help you out. This particular problem, the percent mass volume, we have 8.92 grams over 455 mils times 100. We got 1.96. Now we look at this and you see the grams per mil didn't cancel out, right? So we'd have to have percent and grams per mil. It doesn't matter which order they're in. But usually it's just represented M over V. People know that it's grams and mils. But we have to remember, these units didn't disappear. Now, notice if they'd given us 455 mils of solvent, they gave us just solvent and not solution, right? We could not do this problem unless we knew the density of the KCl. We'd have to know what volume this amount occupied so that we could add them together to get the total solution. Densities, remember, are given in grams per mil. Right? So these compounds have density. That's probably not going to happen, so just wanted to make you aware of that. Solution. All right, I think these are just going to be straight plug and chug. Now you can also use these as conversion factors. What if we had something that said let's say we wanted to calculate the number of grams of sodium chloride, NaCl, containing 85 mils of 4% mass volume NaCl. This is probably how you're going to see it in physio or one of the other biology classes. Right? The first thing we need to do is address this 4%. Okay? Because how are we going to make this 4% this fraction? What's the easiest way to say 4%?
4 over 100.
4 over 100. Yeah. Some people would say 0.4 over 1, whatever. But 4 over 100. So you can change this to 4 grams of NaCl over 100 mils of solution. You can change that 4% to 4 grams over 100. That's 4%. Right? What is this? Conversion factor. Right? That's all it is. Conversion factor. So what do we want to do? We can use it either way, right? We want to write our given information down. 85 mils. We need mils. It's going to be 85 mils of solution, right? We need mils of solution in the bottom. I already had the correct conversion factor. Cancel out mils of solution. We're left with grams of NaCl. What do you get? 3.4. And we have other formulas as well. The formulas are identical to this. The only difference is what we multiply by. So you can copy that down. We get times 1,000, times 1,000,000, and times 1,000,000,000. This is parts per thousand, parts per million, parts per billion. I think that's a lowercase, yes. Parts per billion. So all of those are handled, all of those solutions, all those formulas are handled the same way as our example for parts per hundreds. Right? You don't need to redo those examples. It's this. Just write this same thing in each case. These are one of the ways, a couple of the ways to represent solution concentration. Okay. What's the most famous and most common one? Is molarity. By far. In chemistry, it's molarity. And we've already seen molarity. We saw it yesterday during lab. Molarity. This is a concentration unit that represents moles per liter. Molarity equals the number of moles per liter of solution. For molarity, the volume is specified. It must be in liters. This is a straight up algebraic expression, very similar to density equals mass over volume. We have an algebraic expression containing three variables, capital M, N, and L. That means we can solve for any one of them, but we have to be given the other two, or we have to have a way to calculate the other two. We do have a similar expression to the DMV that I showed you. It looks like this. Okay. If you want to know molarity, cover up M, number of moles divided by liters. If you want to know volume in liters, number of moles divided by molarity. If you want to know the number of moles, you cover up N and the numerator. It's molarity times volume. It's just a simple, quick way to derive things. Okay. take a look at this problem. Calculate the molarity of NaOH in a solution containing 1.25 mole NaOH and 3.12 liter of solution. Go ahead and tell me what my answer is. What is it?
410.
410?
Oh, never mind.
I have 0.40 moles NaOH.
How many significant digits?
3.
Give me it again.
0.400.
What's after that second zero?
1. 4 0.
Do you have a 1?
No, 6.
So do I. So it's not going to round it.
To 1.
Okay. Okay, so our formula, we have molarity equals number of moles over liter of solution, right? This is going to equal number of moles, 1.25 mole of NaOH, 3.12 liter, that's going to equal 0.401 molar NaOH. Notice I took my moles per liter and I changed it to a capital M. Molarity means moles per liter. So we'll see the solution concentration represented as capital M. We've seen that. That's what was on the bottles yesterday in lab class. Right? Capital M. But capital M means moles per liter. So if you have a 3.1 molar HCl, you can take this and go 3.1 over 1 mole liter, and this becomes 3.1 mole per liter. You see how you change that into a fraction? And now you can use it. What is this? What is it? What?
Conversion factor.
Conversion factor. That's what it is. It allows you to convert between moles and liters. Okay? We just did a straightforward calculation where I simply gave you a number of moles and liters, right? So let's kind of mix them up so you can see the different ways that you're going to have to use this particular expression. Take a look at this one. How do you want to do this one? What's molarity?
We don't know.
What's molarity in units?
And then whatever.
Moles over liter, right? We don't have either of those here, do we? But do we see things that we can convert into what we need? Can we convert grams into moles?
Yes.
Heck yeah, we can. That's all we did yesterday, right? Convert grams into moles, moles into grams. Can we convert milliliters into liters? Yes, we can. So we have to do those conversions first before we can get our moles per liter. Okay? There's a couple of different ways to solve this problem. You can do these separately. I can give you a hint. Whenever you have milliliters, just move it 3 places to the left to convert it to liters. Because in order to convert milliliters to liters, you divide by 1,000. Okay? So I can do it. I can understand that my molarity is equal to my number of moles per liter. And I can solve first for my number of moles. I have 28.1 grams of KCl. How many grams per mole KCl? And out of room.
Seven.
74 point what?
5.
74.55? Yeah, I'll go with that. Where did I get this? Periodic table, right? This is the molar mass of KCl. So I get my N, and that equals 0.3769, blah, 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 blah. I don't want to round that answer to any significant digits yet because I only round one time, my final answer. So I'm going to take a look back here and say I need 3 significant digits. Just to be sure, I'm going to take this to 2 more than that, so 5. That way I'll stay out of trouble when it comes to rounding. My liters is 0.750 liters. How did I get that? I have 750 mils. And my conversion is 1,000 mils in 1 liter. That's where I get my 0.750. Can now do some straight up math. This number goes here. This number goes here. My molarity, what does it equal?
.503.
0.503?
0.503
Units?
would be KCl.
Molar,
I'm
right?
sorry.
Okay? So one way is to keep in the back of your mind the algebraic expression and solve for the individual variables, then plug the variables in to the expression and solve it for n. Okay? Another way is to use dimensional analysis, and it's probably a little easier, right? What do you have here? I have 28.1 grams of KCl in 750 mils of solution, right? That's what I have. Agreed? All I have to do is make those units moles per liter. That's all I have to do. So how do I do it? Which one do I want to start with? Doesn't matter. Let's start with the grams and make it moles per liter. Can I take grams of KCl to mole of KCl? Yes, I can. That's what my molar mass from the periodic table does. Something we already have over there. My grams of KCl cancel. I am now left with moles of KCl per milliliter. I don't need milliliter, I need liters, because that's what my formula for molarity says. So I need to convert my milliliters into liters. Now I'm just going to go one set of keystrokes. 28.1 divided by 750 divided by 74.55 times 1,000 equals
0.503.
yeah. Now, why was this one 0.503 and the other one 0.501? Wasn't it?
No?
Oh, it's 503? So exactly right. If we went any further digits, we might have some differences, because remember we took the number of moles to 5 significant digits. We actually rounded it to 5 digits. This method doesn't have any rounding until the very end. Okay, so we can use our dimensional analysis to solve these kinds of problems. Let's change this. One, too small of a number. Let's do 8. Calculate the number of moles of HCl contained in 125 mils of 8 molar HCl. What is our formula telling us we have to do? What? Yeah, what are we going to do then? Do the math. Did you do it? Did you get significant digits?
Oh.
What's the answer? 1, right? 1.0. And calculate the number of moles HCl and 125 mils of 8 molar. A couple of different ways we can do this, right? There's a couple of ways we can approach it. First of all, we can look at our algebraic expression. We can say, what am I looking for? Number of moles. I can cover up number of moles. That's molarity times liters, not volumes, liters. The volume has to be in liters. So I can take my molarity, say my number of moles equals molarity times my volume in liters. This will be 8.0 molar times my volume in liters, which will be 0.125 liters. This is going to equal 1.0 moles to the correct number of significant digits. Alternatively, we could say I have 125 mils of solution. I convert that to liters and I get 1,000 mils, 1 liter, gone. Then I can say I have 8 moles of HCl per liter solution. Liters are gone. I mean, you're going to get good at this where you're going to recognize right off the bat that you can't use that. So you have to change it directly. And if you do that, this conversion becomes much easier. Done. Both cases, it's 1. In all 3 cases, it's 1. One method is showing you how to use dimensional analysis and use your molarity as basically a conversion factor, right? Because if you're asked for moles and you have volume, you can use molarity because molarity is moles per liter. Its whole job is to convert in between moles and liters or between moles and liters. That's the only thing it's good for. So these ones use it as a conversion factor, which is probably going to be the easiest and quickest way for you. But this way, right now, is the more comfortable one. But believe me, you'll get away from it real quick. Okay? If we have moles, we can go to grams, can't we? So we can't get too crazy here, but what if I said calculate the number of grams? Even though it's not technically correct, because HCl is a strong acid and exists in like 17 molar concentration. You can't go and routinely buy solid HCl. Not like NaOH, you can buy it anyway. So let's just play around with this hypothetically for now. How many grams of HCl? Well, if we have moles, we can go to grams, can't we? What's the answer?
36.46.
Yeah, which happens to be the molar mass of HCl, right? Because we only have one of them, right? But you can just take your conversions one step forward. You have 0.125 liters. Oops, I already did that conversion in my head. Liters of solution. I have 8 mole of HCl per liter of solution. This is my 8 molar. Solutions are gone, and I have 1 mole of HCl is equal to 36.45 grams of HCl. I got this from the periodic table. One times H, 1 times Cl. 35.45. And I do that math, and I get 36.45. To 2 digits, though, it would be 36, right? 2 significant digits from the molarity. Whole bunch of different ways you can use molarity. Whole bunch of ways. We didn't do a volume one, did we? Let's do one more. We didn't do a volume. take a look at this. Give me the volume in liters of 3 molar NaOH that contains 0.45 moles of NaOH. Yeah? Good. I'm glad. They're all the same. What? What do we have here? We can use our formula, cover up liters, that's what we're looking for, number of moles divided by molarity, so L, volume, equals number of moles divided by molarity. That's going to be 0.45 mole of NaOH divided by 3.0 molar. 0.15 units? Liters, right? If you want to look at how the units cancel out, you change the M to mole over liter. When you divide by a fraction, you invert and multiply. That's going to put moles on the bottom, which is going to cancel, leaving you with liters in the numerator. So it works out. 2 significant digits, we're good. Okay? How about that little wrinkle? We do the same thing, right? It still equals number of moles divided by molarity. But we see we have our molarity here, but we don't have number of moles, do we? We have grams. So what do we want to do? Yes. You want to convert your grams into moles using the periodic table and the molar mass. Once you have moles, you divide it by 3 and you should be good. Answer? 0.062 liters. How many mils is that? Oops. How many mils? 62 mils. I didn't ask for that, but I could have. What are we going to do? We need N, right? 7.4 grams of NaOH. I have 40 grams of NaOH and 1 mole of NaOH. Got that again from the periodic table, right? Molar mass from the periodic table. Oh, Daddy. .185 exactly. That will go here. 3 molar will go here. And we should get 0.062 liters. Right? Round to increasing them in digits. Alternatively, we can use our dimensional analysis. We can start off with 7.4 grams of NaOH. I know I have a molarity. If I have number of moles, I can get liters because molarity is moles per liter. I have grams, doesn't do me any good. I've got to convert those grams into moles. I am now at moles. I can now use my molarity as a conversion factor. I'm left with liters of solution. Better get the same answer. Yes, you do. This is 7.4 divided by 40 divided by 3. If it's on the bottom, hit divide. If it's on the top, hit multiply. Or you can open parentheses once you hit the divide. Okay, lots of different ways on this molarity, isn't there? Lots of things you can do on this molarity. Dilution. Dilution. What do you do when you dilute something? What do you do when you dilute something? What's that? Thin it? How do you dilute something?
By adding, if you have something that's dark and you add something
Adding more
to
solvent.
it, you could dilute the color.
Add what?
More solvent.
Solvent. Yeah, you add solvent, right? When you dilute something, you add more water, usually, right? That's a solvent. If you add solvent, that means you don't change the number of moles, right? The total number of moles. So if I were to weigh out 58.45 grams of salt, that's 1 mole, okay? And then I were to put salt into a beaker, 58 grams. I would have 1 mole in that beaker, total, right? The concentration would be different because it would depend on the volume. But in terms of solute, I would have 1 mole, right? And then let's say I threw the beaker into the lake. how many moles of salt do I have in the lake? I still have 1, right? The total number of moles doesn't change in the dilution process. The number of moles of solute per unit volume changes, for sure, it changes. If I pulled a little sample of my solution from the beaker and then I threw it in the lake and I pulled a sample from the lake, they would be different. But in terms of the total number of moles, they have to be the same. And this is how the principle of dilution works. There is a dilution formula. It's C1V1 equals C2V2. I've seen this variation so many times. I've seen CIVI for initial, CFVF for final. I've seen CC for concentrated, VC for concentrated, CD for dilute, VD for dilute. So many different ways. Okay, so don't be confused. It doesn't really matter that you identify what the initial solution is or what the final solution is. It is important, however, that you identify which volume goes with which solution. These are very straightforward calculations. This formula is a favorite of students. Because first of all, there are 4 variables here. 2 concentrations, 2 volumes. Because we only have 1 equation, you have to be given 3 out of the 4. 3 out of the 4. So you'll be given 2 concentrations and 1 volume, or 2 volumes and 1 concentration. Alright? Find out which volume goes with which concentration and simply divide it by the other one, and you're done. It's usually pretty obvious which volume goes with which concentration. Now, we can use any unit of concentration that we've used so far. pp, parts per 100, parts per 1,000, parts per million, parts per billion, molarity, percent mass volume, we can use them all, which would be parts per 100. So let's take a look at one that uses percent mass per volume. A good thing about these dilution problems is that most of the time, not all the time, but most of the time, the word diluted or is diluted to or enough solvent is added to form a final volume, you can tell that it's dilution by reading it. Okay? So I'm going to read this problem, and again, I'm not terribly concerned that I identify what's C1, what's C2, what's V1, what's V2, blah, blah. All I need to do is find what volume goes with which concentration and then divide by the one that's left over. So I'm reading this, and it seems pretty obvious to me that 45 goes with 16. Does it to everybody else? Yeah. So I'm going to multiply these two together, and I'm going to divide by the one that's left over. If I wanted to see it algebraically, I would say C1V1 equals C2V2. C1 is 16%. V1 is 45 mils. C2, that's what I'm looking for. V2 is 55 mils. I divide both sides by 55 mils. Cancel the 55 mils, I get C2. My mils cancel. What a coincidence. I'm left with a unit of concentration, percent, mass volume, which is what I was asked for. What do I get? 13%. 13% mass volume, right? To 2 significant digits. These are all done the same way. The only difference, the only thing that's going to change is your unit of concentration. Okay? Be careful with your volumes when you're talking about molarities, right? The number one rule, when you see capital M, your volumes are in liters. When you see molarity, your volumes have to be in liters. Even if they're asking you for milliliters, you have to have your volumes in liters here, you'll solve for liters, and then you convert to milliliters later. All right? You want to do one like that? I can show you. Is everybody good? Okay. Anytime you see molarity, your volumes are in liters. I'm making these up. Totally making these problems up. What's the answer? Got an answer, anybody?
Sure.
What is it?
I got 354.
354?
That's what I got.
354? Let's see. We have C1 V1 equals C2 V2. Now, you see that your volumes are given in milliliters here, and that you're asked for your answer in milliliters. Because they're the same unit, you don't necessarily have to convert these in order to get the right answer. But I don't want you to do that, because I don't want you to develop bad habits. Whenever you have M, you put your volumes in liters. Because it's true, there are certain cases when you won't have to do it with a dilution formula. But every time you use the molarity formula, you do. There are no exceptions there. Okay? So I don't want any bad habits. So I'm going to convert this right off the bat to liters. And I can see that this volume goes with this molarity. So I'm going to have concentration 1 volume 1, I don't know. Concentration 2, 1.25 molar HCl. Volume 2, 0.85. Actually, I didn't have to include that 0, right? Because there was no decimal point to start with there. I'll divide both sides by 3. And my volume 1 will be 0.3541666 liters. I want my answer in milliliters. 354 milliliters. To 3 significant, actually we go 2 significant digits right here. So, but that was easy to miss. 350 mils to 2 digits. 354 was the exact one, but I didn't have a decimal point up here. I meant to, but I didn't. 350 mils. Okay? You will have some dilution problems to solve on the next exam. You will have them on the quizzes. And in fact, we do an entire lab. The next lab is all about creating diluted solutions. Okay. All right. Last thing. Osmosis and osmotic pressure. Osmosis. Okay. In biochemistry and chemistry and most areas of science, you create different gradients. Okay, you can have concentration gradients, you can have temperature gradients, you can have pressure gradients, etc., etc., etc. The best way to explain a gradient that I know is to take a steel rod and heat it up so that it's red hot, for example. And then take another steel rod that's the same composition and touch them together. And when you touch them together, you create a temperature gradient. A difference in the temperature. That's what the gradients are. Now, naturally, temperature flows down the gradient from higher concentration to lower. So the hot rod will get cooler and the room temperature rod will get hotter because heat flows from hot to cold. Most things move down their gradients naturally. There are examples of active transport where things are transported against the gradients, but by and large, things flow down their gradients. And osmosis is no different. In osmosis, all right, you have the movement of water. First of all, you're talking about just the movement of water. No solute particles. It's just water. Now, water will move down its concentration gradient from a region of higher concentration of water to a region of lower concentration of water. Now, it moves past a semi-permeable membrane. Here it is. There's our semi-permeable membrane. And a semi-permeable membrane just means that it's selective as to what it lets cross the barrier. They're very easy to find. Usually things like pig intestines or something like that's a very good source of a semi-permeable membrane. It actually can make some synthetic forms as well. And let's say that on each side of your membrane you have two solutions of different concentration. Let's use sodium chloride because sodium chloride is common. Sodium ions and chloride ions are common. Let's say that we have a 0.5 molar NaCl on one side and a 1 molar NaCl on the other. Which one of those solutions has more water in it? Knowing what molarity is moles per liter. So on one side you have 1 mole per liter. On the other side you have 0.5 mole per liter. So which side has the greater amount of water? Yeah, the one with the lesser concentration, right? The lesser concentration has the lesser concentration of solute has the greater concentration of water. So water will flow across this membrane because there's a concentration gradient with respect to water across the membrane. Water will flow and this will begin to rise. And as water comes across here, it actually dilutes this. Right? As water flows across, it dilutes this concentration and concentrates this solution. Right? And this will happen until you have equal concentrations on both sides. Right? You would suspect that that would happen when both of them are at about 0.75 molar. That's what you would suspect. It's halfway in between. Okay? The amount of pressure that you have to apply to the surface of this side of our vessel to prevent the water from going up is called the osmotic pressure. That's what osmotic pressure is. It's the amount of pressure that you have to apply to one side of your system to prevent the flow of water down its concentration gradient. That's osmotic pressure. Straight and simple. What's confusing about osmotic pressure is that sometimes it's defined as the flow of water from a region of low concentration to a region of high concentration. That's what's confusing, right? Because when we talk about concentrated solutions or solution concentration, we don't talk about it in terms of solvent. You might not have thought about that through this entire lecture. When we're talking about solution concentration, it was always solute. Solute, solute, solute. We don't think of it in terms of solvent. So when they're talking about the flow of water from a region of low concentration, they're talking about low solute concentration, which would be the higher water concentration. It's just a little bit of backwards talking in terminology. So these concentrations here are solute, not solvent. Low concentration here would be high water. High concentration would be low water. So when you're talking about water going from a region of low solute concentration, you're still talking about it running from high water concentration. That's the confusing part about osmotic pressure. And it will flow across until the two solutions are equal. Okay? Now the osmotic pressure is only dependent on the number of particles. It's not dependent on the identity of the particles. Right? Just the number. So we can calculate an osmolarity, which is similar to molarity that we just calculated, only instead of it being solutes, molarity being solute per liter of solution, osmolarity is osmoles. Right? And osmoles are a little bit different than molarity. Osmoles are just the number of moles of particles that contribute to osmotic pressures. It's technical definitions. But we can calculate an osmolarity by taking the molarity of the solution and multiplying it times I. So the hardest thing we're going to have to do is determine what I is, which is the number of particles. It's the number of particles. In our questions, you'll be given molarity and you'll be given a formula. So what you're going to have to do is dissect the formula and figure out how many particles there are, because the molarity is going to plug directly in. So let's take a look at one. Let's do calculate the osmolarity Let's calculate the osmolarity of 0.15 molar sodium sulfate. Our formula is osmolarity, abbreviated OSM, equals molarity times I. The molarity is given, so that's no big deal. But what is I for sodium sulfate? It's 3. How do you know that?
Sulfate is SO4 is 1.
It counts as 1 because it doesn't break apart, huh? Did you guys say, well, you see that it's an ionic compound, right? So you know that the two sodiums are going to break up. The question is, does the SO4 break apart? So do I have 2 sodiums, 1 sulfur, 4 oxygen, in which case it would be 7? Or do I count the SO4 as 1 particle? The answer is SO4 is a polyatomic. These are 2 nonmetals. It's a covalent bond. SO4 does not break apart. So it's counted as 1. So I, in this case, is equal to 3. The 2 sodiums and the 1 sulfate. And they both influence osmotic pressure equally, even though this thing is huge compared to this. It only depends on the number of particles, not the identity. So this would be 3. We multiply that by 3, we get 0.45 osmol, right? That's an M. So you'll see some of these calculations. And the only thing, or the most difficult thing you're going to have to do is determine what I is. Just know for ionic compounds with a metal, separate off the metals, keep the polyatomics together, add them all up. For a compound that contains only nonmetals, it's a covalent compound, I is equal to 1. So that sugar that we did earlier, C22, or C12H22O11, that would have an I equal to 1. Because it's just one big molecule. It doesn't break apart. Okay? You good? One more? All right. What do we have? Osmolarity equals molarity times I. Our molarity is 0.5. What is I? 4. We have 3 lithiums, 1 phosphate, 4. Two. Good?
I'm trying to understand where we got the 4 from. Like I'm seeing it, I'm not completely understanding.
Well, let's imagine that this is what the lithium phosphate looks like in a crystal form, okay? It doesn't, but let's imagine that we have the phosphate here, right? And then you have these lithiums hanging off, right? Li3PO4. And you know why there's 3, because Li is plus 1.
Yes.
and PO4 is 3 minus. So you need 3 lithiums to make a neutral.
Okay.
So I break this apart. How many particles do I now have in solution? 4. These don't break apart because they're covalent.
Okay.
You break the metals off, but you keep the polyatomic ions the same. They only count as 1 particle.
Can you do one more then?
Yeah. Why are you looking at the periodic table? Why? No, just the particles. That's all that counts. And the charges, you already have the formula. NABR is the formula, right? When it breaks apart, what's it going to break apart into? That's where you get I from. Has nothing to do with chart. We already gave you the formula. Right? So, this one, I is equal to 2. So our osmolarity equals molarity times I, 0.025 times 2, 0.050, right? Osmol. I think she's got it. What's I? Say it. What's I? What's I for K3PO4? 4. 3 Ks, 1 PO4. 3 plus 1? 4. How about if this breaks apart, what do you get?
1 and 1. No, 2. So 3.
3. It's I.
And 4. 5.
When she finally gets it, she can say, "Wow!" Look at these are polyatomic ions, right? This I is 2 because magnesium and SO4. I is 2. We got 1 here. I is the number of particles. That's all it is. It's the number of little particles floating around. It doesn't. Osmotic pressure doesn't depend on the identity of the particle. It just depends on how many you have. SO4 is considered 1 particle because the sulfur and the 4 oxygens float around together as one unit. So it only counts as one blob floating around. The magnesium only counts as one. The PO4 only counts as one because they're hooked together. They don't break apart. The potassiums do break apart, each one. So you have 3 potassiums, 1 PO4.
How do you know which one breaks apart and which one?
The polyatomic ions don't break apart. The metals do. See, these are metals. Potassium's a metal over here. And the polyatomic ions, we have an exam today. You better know those, right? Metal, non-metal, polyatomic. Right?
The NH4 does not break apart.
That's right.
So it's 1.
How many do we have?
1.
How many do we have?
2. And then does the O count as 1? also?
Breaks off in O negative 2.
So 3.
3. This one's not a good example. This one's totally covalent. That one's actually not a good one at all. I was just trying to give you an example of a positive polyatomic. Ammonia's the only one. How about
The AL is 1. And CL is 3. So it's 4.
yes.
Oh. I think I get it.
Got it? Right. It's going to have to do some problems, right? Next example.